So what we're talking about today is lesson 5.4. We're going to talk about some exponential growth and exponential decay. So this is related to equations that we have worked with already at the beginning of this chapter. These are equations in the form of y equals a, which is your initial value, times b, which is the rate in which you are changing, to the x power, x representing some form or amount of time that you are changing by, or that you need to find the growth or decay of. So we're going to kind of just jump in and see how it works with a word problem, make sense of what this means. So the half-life of a radioactive substance is the length of time it takes for half of the atoms in a sample of that substance to decay. So here we're talking about decay. So we're getting smaller exponentially. Okay, so decay. Carbon-14 has a half-life of 5,730 years. Wow, how long is that? Suppose you have a sample of 10,000, so we're starting with 10,000 carbon-14 atoms. How many atoms will be left after 17,190 years? Explain your reasoning. Well, let's look at this. What do we know? Well, we know that we have an equation in y equals a times b to the x form, so we could always use f of x, just function notation. So equals a, our initial value, times, well, since we're talking about a half-life, we're going to use 0.5 to the x power. All right. So our a value is our initial value, which is 10,000 atoms, and then x is half-life periods. How do we figure out how many half-life periods are in 17,190 years? Well, we do 17,190 divided by the years in a half year. So, or half-life. I'm so sorry, half-life. So divided by 5,730 years. What do we get? Well, we get that x is going to equal, in this case, 3. So I put all my known information together in a function. So a, my initial value, is 10,000 times 0.5, the half-life, to some exponent of time, which is x. But now we know x is 3. So we plug in 3 for x, and we find out that after 17,190 years, we have 1,250 atoms. So this is the basis of what we're doing today with exponential growth, and then we'll be looking at exponential decay. So this was decay, okay? So we got 0.5 because it's a half-life. Half of 1 is 0.5. So let's focus our information now on exponential growth. So exponential growth can be modeled by the function y equals a times b to the x power. So I'm going to highlight that for us. Y equals a times b to the x power, where a has to be greater than 0 and b has to be greater than 1. The base b, this is important, is our growth factor in this case, which is equal to 1 plus the percentage rate of change, but we write that as a decimal. So this looks like this. So you have 1 plus percent as a decimal, and this would be equal to your b value. So for growth, b equals 1 plus the percent you're growing as a decimal. So this kind of maps it out for you. This is very good to know. I hate to say memorize, but memorize would be a good word here. This right here, all this great information. Okay. So the initial amount is A, like we talked about. B is your base, of the exponent, which is greater than 1, and this is how we find b right here. B is 1 plus the percent as a decimal, and then x is your exponent. And then to the right, we have a graph of a general exponential growth equation. All right, here we go. So we are going to put this, oh, I'm sorry, we skipped over a few. So we are going to put, we're going to put this into practice. Sorry, I had to find example 1. So since 2005, the amount of money spent at restaurants in the United States has increased at about 7% each year. And in 2005, about 360 billion was spent at restaurants. If the trend continues, about how much will be spent at restaurants in 2015? So we need to find our initial amount. What are we starting with? Well, it says in 2005, about $360 billion was spent. That is our starting point. 360 billion. Now we have to find our B. Well, we know we're growing. This is a growth factor because it says over here it says increased about 7% each year. But remember, it has to be a number greater than 1. So we take 1 and we add that 7% as a decimal. So 1 plus 0.07, which gives us 1.07 as our B. So now I'm going to combine this, and we're going to get an equation. So my initial amount goes in the first slot, and my growth factor goes in the second with an exponent of x. So we have an equation of f of x equals 360 times 1.07 raised to the x exponent. Okay, so what is x? Well, x represents the amount of time from 2005 to 2015. So x in this case would be 10, because there's 10 years to get from 2005 to 2015. So we're going to plug all this information now into our equation, and we get f of 10 is equal to 360, our initial amount, times 1.07, our growth factor, raised to the 10th power. So we have to show our work, but in this case, you guys have calculators handy. So when you type this into your calculator, type it in all as 1 and save your rounding until the very end, okay? So in 2015, about $708.17 billion will be spent in restaurants. Wow, that's a lot. So example 2, we're going to jump right in. We're going to try this. Suppose that in 1985, there were 285 cell phone subscribers in a small town, very tiny. The number of subscribers increased by 75% each year after 1985. How many cell phone subscribers were in the small town in 1994? So we need to look at some of our information. What do we know? Well, what's our initial value? What are we starting out with in this case? Well, we're starting out with 285 cell phone subscribers. All right, well, what are we growing by? So we know we need 1 plus, the growth rate is 75%, but as a decimal, it's 0.75. So our growth rate is 1.75. So we get an equation of f of x equals 285, our initial amount, times 1.75 raised to the x power, because we don't know the amount of time quite yet. So let me put my multiplication symbol in. All right. So we have this equation. Remember our initial amount. So A, and this is our B. This is our growth factor. Okay. So X. What's X? X is our time. It says how many cell phone subscribers were in the small town in 1994? Well, how much time passed from 1985 to 1994? Well, that's how many years? We have 9 years. So we have all our information organized right here. So we do have growth in this case. So I should have highlighted growth because it says increases. Okay. So with that being said, we are going to plug in. We have a missing variable of x, but we know x needs to be equal to 9. So I rewrite my equation. I have that when I type this into my calculator, f of 9 is equal to 285 times 1.75 to the 9th power. I get 43,872. Well, what does that mean? What's that number? That number says that in 1994 there were 43,872 cell phone subscribers in the small town. So remember, the equation that we are continuously plugging into right now is y equals a times b raised to the x power. And we're going to continue to use this. But there are some special cases that we might need to work with. So this is our general formula, and we always expand off of this general formula, whether it's growth or decay. So, but we do have special cases, and compound interest is what's used for bank accounts and investing money and finding out how much money you're going to have way down the road. So let's talk about this. The definition of this special case is that when a bank pays interest on both the principal balance and the interest on the account, and the interest an account has already earned, the bank is paying compound interest. So they're taking the amount you have in there, they're adding in the money you've earned over time, and then taking an interest rate of the money that you have all combined. All right. So compound interest is a special case of exponential growth, and for compound interest we have a special formula. So if you look below, you have to know these. So let's start talking about them now. A is your balance. This is the final balance after you're finding an amount. Okay, so A is the balance. P is the principal amount. This principal means this is your initial deposit. How much are you putting into that bank account? Say you're putting in $200. So your principal is your initial deposit of money. R is the annual interest rate. So are you going to make 10% off this account each year? Are you going to make 2%? But that's for this right here. And it's important that this is expressed as a decimal. All right. So your rate would be a percentage that you have to transfer into some type of decimal. Then we have N. N is the number of times the interest is compounded per year. So we're talking about in years here. So it could be compounded monthly. So that would be 12 times in 1 year. It could be compounded bi-monthly, which would only be half a year. So it would be compounded 6 times out of the year. Okay. And last but not least, T is our time in years. So it's important that this formula is based around the measurement of time in years, not in months, not in weeks, not in days. So we need to compensate for that. All right, so please refer back to this as we are doing examples. It will be helpful. Rewriting them a few times could help as well. So let's try to apply it. Suppose that when your friend was born, your friend's parents deposited, that's a key word, $2,000 into an account, paying an interest rate of 4.5% compounded monthly. Remember, we just talked about this. the equation is based in years, but they're talking compounded monthly. So if I compound it monthly, how many times a year is that? Well, that's 12 times. We have 12 months in a year. So compounded 12 times. And we want to know the balance after 18 years. See, there's that years again. So what's my initial deposit? Well, my initial deposit right here is $2,000. What is my interest rate? What is the percentage that I'm gaining money? Well, we have to write it as a decimal, so 4.5% is still written in percentage form. So we have 0.045 as our decimal. How many times a year was it compounded? Well, it said compounded monthly, so that's every month. And in a year, that would be 12 times. And what's our T here? What are they asking us about? They want to know for 18 years. So I have an 18 there. Okay, so I rewrote the formula that was presented to us. We're going to plug directly into this formula. So 2000 is going to go in for P, 0.045 is going in for R, 12 will go in for N, both of them, and 18 will go in for T. So let's show some work. Here's my plugging in. This is my first step. So if you would like to label your steps, this step, sorry about that. This step right here is plugging into the formula. So let's make this fit a little bit better. So we plugged into the formula. All right, after plugging in, I simplified a little bit this part right here. See how I took that fraction and just created a decimal out of it. I didn't round the decimal. I wrote the exact decimal in, and I plugged in on my calculator. After you plug in on your calculator and hit enter, you get that there is $4,489.01. So my final answer comes to, after 18 years, the account balance is $4,489.01. So the difficulty here is memorizing the formulas. Once you have those memorized, the plugging into the formula is easy. It takes some practice. So what I want you to do now is pause the video, try this one out on your own. All right, I kind of set up the problem for you. I did some annotating. Now you try this one all on your own. How do you set this up? What's my final answer? And what is the answer as a complete sentence? So go ahead and pause the video and then come back. So to check your work, I'll show you what it looks like here and my answer in a complete sentence. All right, now that you had some practice on your own, we're going to go on to exponential decay. So this one's a little different. Exponential decay. So for exponential decay, we're using the same formula. Y equals a times b to the x, where a is greater than 0, and b, in this case, has to be between 0 and 1. So b is your base and your decay factor. So which equals, this is important, 1 minus the percent rate as a decimal. So this is just the opposite of what we did for growth. So let's write this down. Make sure you have this. B is equal to, for decay only, 1 minus percent as a decimal. Okay, this is your decay factor now. So from here, it re-emphasizes the equation that a is your initial amount, x is your exponent, and the base is the decay factor, which is b is equal to 1 minus the percent as a decimal. To the right, we have the graph of a decay factor. We start with a very large amount, but then we start getting smaller and smaller and smaller and smaller, and we get super small. That's why it gets so close to our x-axis. So let's try it. We're plugging right into our equation. The population of a city is 45,000, and it decreases. So we're talking about decay again here. It decreases 2% each year. If this trend continues, what will the population be after 15 years? So as I went through, I labeled the important information. 45,000 is A, your initial amount, decreases by 2%. I'm already thinking in terms of decimals, so I just changed it to a decimal right away in the story. If the trend continues, it wants to know the population after 15 years. That is my X value. So initial amount, 45,000. B, I have to do 1 minus the percent as a decimal, 0.02. I end up with 0.98 as my B. That's important here. 0.98 is my B. So the equation with all this put in except for X would be my initial value, 45,000, times my decay factor of 0.98 raised to the X power. So I know X should be 15. I'm going to plug that in and I'm going to show my work. So I plug in to this general equation and I get 45,000 times 0.98 raised to the 15th power. I plug in on my calculator and I get 33,236 with a final answer as a complete sentence. After 15 years, there will be 33,236 people. All right, so let's practice again. I'm going to let you try this on your own using the same method we used in example 5. So the kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meter increase in altitude, the pressure decreases about 11.5%. What is the atmospheric pressure at an altitude of 5,000 meters? So go ahead and pause the video, try this one on your own, come back and check your work with mine. So as you can see, I've labeled all of my information and I showed all my work. So my last example, we're kind of talking about something different. Instead of trying to write an exponential growth or decay formula from a story problem, we are going to write these from a table and or a graph. So first, you need to find the starting point. What is our A value? So we do this by looking at where X is 0. When X is 0, that allows us to find out what that initial value is. So I'm going to highlight that. So to find A, look for when X equals 0. So I can write that down so we don't forget. To find A, we look at when X equals 0. All right. All right, how do I find my B? How do I find what I'm changing by? Well, this comes back to what we were talking about yesterday when we were finding out if an equation was exponential or linear. What are we changing by every time? What am I multiplying by here? I have to have some type of constant multiplier. In this case, my constant multiplier is 1/4. So that's the rate at which I am changing. My constant multiplier is my b value. So something else we can add to our notes. Let's move that out of the way. The constant multiplier that we find is our b value. It is the base. It is the base of our exponent. So make sure you write those down on your notes. These are important. There we go. All right. So those might be some good things to study. Now let's look at our graph. Where is it to find the a value here that we were talking about? We need to look when x is 0. So I'm going to go to the graph and I'm going to find the point when x is 0. So x is 0 here. Here's my ordered pair. All right, so when x is 0, we have a 2. So my a value, my starting point in this case, is 2. Okay, how do I find the base of my exponent? What am I changing by every time? Well, it's nice because on this graph they provided these perfect points for me. So 0, 2, 1, 6. So how did I get from 2 to 6? Is there a constant multiplier here? If so, what is it? Okay, well, 2 times what gives me 6 is what I'm asking myself. So 2 times question mark equals 6. Well, in that case, it would be 3. So that constant multiplier in this case works out nice. It is times 3. So we have the function f of x equals 2 times 3 raised to our exponent. All right, so for the rest of the weekend, have fun. On Monday, we will practice what we just looked at in our notes. All right, you guys have a great weekend.